Hello dear students, Assalamu alaikum. I hope you will be fine. I am Engineer Mir Masood Shah. I am lecturer in Department of Technology, Saraj University of Science and Information Technology, Peshawar. As I am teaching you the subject design of hydraulic structure, today is your lecture number 8. In lecture number 8, we will study about Khosla theory. As we already started about the topic seepage theories, so this is the third theory, which is Khosla theory. We have already studied about leaks theory and lens theory, and in this lecture we will study about Khosla theory. The seepage water does not creep along the outline of the hydraulic structure as stated by Bleek, but on the other hand, this water moves along a set of streamlines. We have already studied that Bleek stated that the seepage water creeps along the hydraulic structure, outline of the hydraulic structure, but Khosla says that it moves along the set of streamlines, not along the outline of the hydraulic structure. This steady seepage in a vertical plane for a homogeneous soil can be expressed by Laplacian equation. The steady seepage for homogeneous soil in a vertical plane is expressed by Laplacian equation, which is d square phi divided by dx square plus d square phi divided by dz square equal to 0, where phi is equal to flow potential, which is equal to kh, and k is the coefficient of permeability according to Darcy's law, or as defined by Darcy law, and h is the residual head at any point within the soil. The wave equation represents two sets of curves intersecting each other orthogonally. The wave equation represents curves of two sets which intersect each other orthogonally. Orthogonally means at right angle. The resultant flow diagram showing both the curves is called a flow net. The diagram which is made by these two curves is known as flow nets. Here, these are the lines which moves beneath the structure, or streamlines which move beneath the structure according to Khosla theory, and the seepage occurs through these lines. Also, here these are the equipotential lines, the lines of equal residual heads. When these lines joins each other, they represents a flow net, or the combine or the resultant of these flow lines showing the flow net. This is called the flow net. Now, streamlines. The streamlines represent the paths along which the water flows through the subsoil. So streamlines are the lines through which the seepage water flows beneath the structure or in the subsoil or through the subsoil. Every particle entering the soil at a given point upstream of the work will trace out its own path and will represent a streamline. Every particle entering the subsoil on the upstream side, they will move through these lines or will trace its own path beneath the structure and will represent a streamline. The first streamline follows the bottom contour of the work and is the same as Bleek's path of creep. The first streamline, according to Khosla theory, follows the Bleek's theory and it moves along the bottom contour of the work. while the remaining streamlines follows smooth curves transiting slowly from the outline of the foundation to a semi-ellipse as shown below. While the remaining streamlines follows smooth curves and they slowly transit from the outline of the structure of the foundation to a semi-elliptical shape as shown in the figure. So the first one moves along the contour of the structure following the Bleed's theory or Bleed's path of creep, while the remaining follows smooth curves transiting slowly from the outline of the foundation of the structure into a semi-elliptical shape as shown. The space between streamlines and equipotential lines is called a field. An equipotential line represents the joining of points of equal residual head. The points at which the residual heads are equal represents an equipotential line. For example, this is an equipotential line. So, on all the points on this equipotential line, the residual head will be equal. So, the points at which the residual heads are equal represents an equipotential line or represents an equipotential line. Hence, if piezometers were installed on an equipotential line, the water will rise in all of them to the same level. As equipotential line represents the joining of points of equal residual head, so if piezometers were installed on this equipotential line, the water will rise up to the same level in all of the piezometers. As shown in figure, this is the equipotential line, and piezometers were installed in 3 piezometers were installed in this or at this equipotential line. You can see the water rises up to the same level in all of the 3 piezometers, showing the equipotential line. So equipotential lines are the lines in which the residual head are equal at every point. Now, exact gradient. The seepage water exerts a force at each point in the direction of flow and tangential to the stream lines as shown in figure above. As the water seeps, it exerts force on each point in the direction of flow, which is tangential to the stream lines. These are the forces as shown in figure. They are tangential to the stream lines. This force F has an upward component from the point where the stream lines turns upward. As this force F has an upward component from the point where it turns upward. This is the streamline and it moves, and as it turns upward, it has a component, vertical component, having force F. This force has the maximum disturbing tendency at the exit end. This force F has the maximum tendency at this exit end. This is the entering end, while this is the exit end. So it has the maximum disturbing tendency at this exit end, because the direction of this force at the exit point is vertically upward, and hence full force acts as its upward component. So because as this force has maximum tendency at the exit end, this vertical force, because the direction of this force is vertically upward and full force acts in the upward direction, so that's why their tendency is maximum at the exit end. For the soil grain to remain stable, the submerged weight of the soil grain should be more than this upward disturbing force. So here at this point, for the soil grain to remain stable, their weight should be, or their submerged weight should be more than this upward pressure to remain stable. Means the weight of the submerged soil should be greater than this upward force to remain stable. The disturbing force at any point is proportional to the gradient of pressure of water at that point. This gradient of pressure of water at the exit end is called exit grade. So the disturbing force is proportional to the gradient of pressure at any point of water at that point, and this gradient of pressure at that point of water at the exit end is called exit gradient. In order that the soil particle at exit remain stable, the upward pressure at exit should be safe. In other words, the exit gradient should be safe. Next is critical exit gradient. The exit gradient is said to be critical when the upward disturbing force on the grain is just equal to the submerged weight of the grain at the exit gradient, at the exit. So the exit gradient is said to be critical when the weight of the submerged grain at the exit end just equal to the weight of the upward disturbing force. So at that point the exit gradient is said to be critical. Means this is the exit gradient. So at that point, when the upward force equal the submerged weight of the particle at this exit point, so in that condition the exit gradient is said to be critical. And this is the end of our today's lecture.